Uh, Thank you everyone for joining today. So our today's speaker is Professor Sin Lawton from George Mason University, and he will be talking about some results about important and character variety. Mr. Lawton, please.
Oh, yes. Hi. Okay. Thank you so much for having me. It's a pleasure to be in India. uh, since of course, we're virtual. I appreciate the invitation and everything. Okay. So let's see here. So I'm going to tell you about a recent paper that is in collaboration with J-P Burelle. It's called Dynamics on Nilpotent Character Varieties. And here's the archive listing if you want to read more about the paper. So let's basically, what I'm going to do is I'm going to illustrate the main theorem, or one of the main theorems in this paper, by an example, and just kind of go through that example in detail. And then I'll end with stating the general result. Okay. Please let me know if there's any questions. All right. So we're going to begin with defining a group. So we're going to let H be the Heisenberg group. So we have 3x3 matrices of the following form, such that X, Y, and Z are in the integers. Okay. So this is sometimes called the discrete and 3D Heisenberg group. Okay, so H is a group under matrix multiplication. And what else is about it? What can we say about it? It is non-abelian. You can multiply two matrices and check that for yourself. And more interestingly, if we look at the commutator of the commutator, then actually it equals 1. So that implies that H is, in fact, nilpotent. Okay, so if you have a sequence of these, iterative commutators eventually trivializing, then that's what it means for a group to be nilpotent. So we see with this particular one, it happens after just 2 steps. So you take the commutator, then you take the commutator of the commutator, and then it stops. So this was actually called 2-step, because it only takes 2 steps in that process. 2-step nilpotent. Okay, so in fact, we can say a little bit more. In fact, H is isomorphic to a free group quotient by the commutator of its commutator. And that gives a presentation for H in terms of 3 letters, A, B, and C, such that A, B, A inverse, B inverse, that's the commutator. Times C inverse is the identity. And then A commutes with C, and also B commutes with C. Okay, so in particular, C is central. Now, the outer automorphisms of H, you can do a calculation, that is going to be isomorphic to GL to Z. Now, I find that people often forget this, but GL to Z doesn't mean 2 by 2 matrices with integer entries that are invertible, it means 2 by 2 matrices with integer entries, so that the determinant is a unit in Z. So that means the determinant is plus or minus 1. So it's closer to SL2Z than it is to what you might think of like GL2Q or something. But anyway, okay, just pointing that out. Most people want that reminded. Okay, so out is isomorphic to this and acts on H. So how is it, it acts as automorphisms, right? So how is it acting? We can say very specifically. So if I take an element in GL2Z, and I want to know how it's acting as an automorphism. Well, so a general element of the Heisenberg group has this form. And so what do you do? It's really just linear algebra. This part of it is fixed, okay? The central part, because it's an automorphism, has to go to the center. So it goes to, right, plus or minus Z. But then what happens to X and Y? Well, if we think of X and Y as a vector, right, and you think of G as an element of, right, 2 by 2 matrices, then you just do matrix multiplication. And then you take the first component of that result, because the result was a vector, right? And then here you just do the opposite. So you take matrix multiplication with this vector, and then you just take the second component. Okay, so that's what the action looks like. Okay. Any questions so far? So basically, so far, just talking about the Heisenberg group and some of its properties. All right. So now, so H mod its commutator. Well, if we got rid of the center, essentially, we're left with, so look at that presentation here. Right, we have 3 things, right? But then we quotient out by the commutator, and you're really just left with the A and the B. So, but then you've made it abelian, okay? And so now you have 2 generators. The relations all trivialize when you make it abelian, and so it's just the 2. Okay, since H is 2 generated and 2-step nilpotent. So thus, there exists a surjective group homomorphism H, just call it pi, to the abelianization of H, which is C mod 2. Okay. Now this is sort of backwards a little bit, but I just want to point out here that this is another way. This is one way to see this isomorphism here. Okay. So if you take an automorphism here, then it corresponds to an automorphism here through this map. And basically this shows that there's a surjection this way, but then you have to show that in this case it's injective too, but that's it's an additional step to do. But this map is really the beginning of coming up with a proof of this fact. Okay. All right. So yeah, I think that's probably a good place for me to make a section divider there. So the first thing we talked about was, we could say section 1. We could say section 1, Heisenberg group. Okay. All right. So our next section 2, is about a Lie group. So this is SU2. That's the one we're going to care about. All right, so most of us probably know what SU2 is, but I'm going to remind you. Anyway, so you just take pairs of complex numbers and you arrange them into a 2x2 matrix such that the determinant, which if you write down the determinant, it's just this, equals 1. Sorry, I got the camera in the way of my iPad. Okay. All right. And so these are determinant 1, 2x2 unitary matrices. And so you can explicitly parameterize them as such. And you can see A, B, C, and D are real numbers. You can see from this description that you just have 4 real numbers that satisfies this A squared plus B squared plus C squared plus D squared equals 1. And so this is clearly a 3-sphere. Okay. It's also, incidentally, I don't actually need this, but the unit quaternions, which is just, quaternions A plus IB. It's just a different way to organize the information such that they're unit norm. Anyway, that latter fact I'm not going to need. It's just a side comment, really. Okay, so what are we going to do with? So we have two ingredients. We have, we have a discrete group, the Heisenberg group, and we have a Lie group. So that's a group with the structure of a differentiable manifold, and we can see immediately what that manifold structure is. It's a 3-sphere. Okay, and so what we're going to do is put that together and consider the space of homomorphisms. So I guess I'm switching topics here, but anyway, that's fine. I'm not going to create a next. Maybe I will. Section 3. Okay. Section 2 was short. Okay. All right. So now consider, we'll use a math cal here, calligraphy. The set of homomorphisms. R stands for representations. So you could think of these as representations because SU2 is linear of H. So this is the set of homomorphisms. And so far it's just a set. So given the presentation that we talked about in section 1 of H, R is determined by pairs A, B in SU2 to the second power, okay, such that, well, the relations hold, right? Where are the relations? I put them here. So that these relations hold, okay? Oops. So such that if you take C, which you define to be AB, we have the condition that CA is the identity. So this is the 2x2 identity matrix. And this is also equal to BA. Okay, so let's just remind ourselves of that, right? So this relation here demands that C is the commutator of A and B. So if I know if I have two matrices, if I want to determine a homomorphism, I just need to know where the generators of H go, right? H has, with respect to this presentation, 3 generators, A, B, and C. So if I associate the first one to a matrix, right, in SU2, and in the second one, this relation tells me that C is completely determined. It's determined as the commutator of A and B. And then I need the 3 matrices, A, B, and C, capital A, B, and C, right, to satisfy these conditions. Okay, so that's exactly what I wrote here. That for any pair, if I associate C to be the commutator, I need to demand that these two conditions hold, that C commutes with A and B. And that will be true for any homomorphism. So if I take a
The
homomorphism.
last one will be, sorry, so last one will be C comma A, B comma C.
Oh, yes, of course.
Oh.
Yes, thank you. Totally messed up there. Yes. Yeah, exactly. Thank you very much. What was I saying? Oh, yeah. So if I have a homomorphism, then, right, I get such a triple, or I get such a pair that satisfies this condition, okay, because it has to satisfy, right, the relations of H. And conversely, if I have such a pair that satisfies these, then I can just, since it's a group homomorphism, I can then define a homomorphism by, extending the identification. Little a goes to big A, little b goes to the big B, and little c goes to big C, to just satisfy the, the condition to be a homomorphism, that it preserves products. Okay, this is generally called evaluation. Okay, so what is the upshot of this? So thus, R can be thought of as a subset of SU2 to the second power, which is just S3 cross S3. And so we can and do give R the subspace topology. Okay, so in other words, we started off a priori just with a set of group homomorphisms, but using the evaluation map, we can identify this set with a subset of a manifold, and we can then therefore give it the subspace topology. So we've topologized this set. Okay. All right, so now that we have a topology, we can talk about topological things. So let
one question.
R0. Yeah, go ahead. Yes.
Yeah, so if I consider just so the H has its own topology from matrices, right? Probably discrete topology.
Yes.
And
Yes.
so
Yeah, it has.
Yeah, so if I consider simply this compact open topology, will it be different?
Yes.
Here?
Yes, it's the same.
Oh,
Yeah,
it's the
that's
same.
fine.
Okay.
Yeah, it's the same. It's homeomorphic.
Okay.
Yeah. So if I give this discrete topology, and I use this, this is the topology of the Lie group, and I consider the compact open topology on this, then that gives me this a homeomorphic topology is doing this, this thing of the subspace topology under evaluation. Yep. Good question. Yeah, it's an intrinsic way to do it. But anyway, it's more mysterious though. It's more natural. It's more intrinsic. It's intrinsic, and so maybe more natural to do that. But it's more mysterious because then you're like, what does it look like? But when you see it externally, you kind of say, oh, okay, it's living inside a pair of three spheres, and I can start to think of it as a subspace explicitly, and so I kind of like that better, especially for presentations. But anyway, okay. I think actually in the paper that I'm referring to, we do it the other way because we're doing it more generally, right? For arbitrary nilpotent groups and arbitrary compact Lie groups, which is where I'm headed eventually. But anyway, so right now I'm just building up the objects that the theorem concerns, and then I'll tell you what the theorem looks like, and eventually. Okay. All right. So anyway, so now that we have a topology, we can consider the connected component of the identity. So let R naught be the connected component of the trivial homomorphism. So what do I mean by that? That's the one that sends, A to the, well, I guess I use the notation 2 by 2 there, right? B goes to that as well, and C goes to that as well. Okay, all right. And this is a little warning. don't know if red is Bourbaki warning sign here. R is not connected. If you so it's in this case, I mean, in more generality, we consider more general Lie groups and more general nilpotent groups. There are some cases where the space would be connected, but most of the time it's not going to be connected. And in this
Do you
particular
know?
one, it's not connected. But in this particular one, it is not connected. So we are picking a special group.
So one
Yes, go ahead.
question. That so how many connected components are there?
In this case, that's a good question. Actually, I forget. It's known in this case. I think it's just 2, but
yeah,
it's known in this case. I just forget what the number is. But in general, for nilpotent groups, it's not like, I don't think there's a formula known. I think you have to like look at specific nilpotent groups to address it.
But will it always be finite or something?
Oh yeah, it's definitely finite. I mean, as long as the Lie group is compact, it doesn't even have to be nilpotent. Any Hom space will have a finite number of components. It's because the Hom space will be compact too, because it's a semi-algebraic subspace of a compact space, and so it's going to always be. It'll always have a finite number of components. And so but for the Heisenberg group, it's known. I think it's even in our paper, like as we talk about the dynamics on the full space, and we look at the I'm trying to remember. Let me just say I don't know, because I don't remember off the top of my head. I know we address some of the cases where it's disconnected and look at specific examples, but I don't remember off the top of my head. Anyway. But I know there's at least 2. And I think for this particular one with SU2, I think it probably is 2, but I'm not 100% sure. Okay, let me just leave it at that. It's a good question though. Okay, so what can we say about this component though? So we're going to let T be the maximal or a maximal torus, or maybe your favorite incarnation of it inside. Inside SU2. Okay. Then HT, and we should just note here, this is just a circle. Okay, so this is right. This is homomorphic to this S1. Okay. This is, well, because T is abelian, it actually is equal. It factors through, but actually equals the set of homomorphisms through the abelianization, which we already saw. Maybe I should put I think in this case I probably should put isomorphic, but okay. Is the free abelian group of rank 2, which again, because T is abelian, is just T squared, which is of course just S1 cross S1, just a torus, friendly torus.
Your voice,
Yeah.
There's a lot in your voice is not audible.
You can you hear me now?
Yes. No.
Yes.
Sorry, I might have mumbled something. Sorry, I was I was shading in my torus. So I got distracted maybe. Okay. Okay, so right. Now so moreover, since T is S1, we already said that. That implies that HT is a subset of the identity component. Why? Because the the homomorphism where A, B, and C map to the identity. Well, the identity matrix is in T. Okay, and so that implies, right? Okay, and so the identity is in there, but then what's the point here? This is connected, right? Because we've identified it with, like a connected space. So you have the identity representation is here, and this is connected, and so that implies the whole thing is in here. Okay, so we've identified a big subspace of R0. Okay, now with more work, we can actually, we can show that R naught, let me write it, hold on here. R naught is homeomorphic, and I'll write it this way. There's an arrow here, iota, to the set of homomorphs from the abelianization, which is, well, maybe I won't write that. I'll just write a different color here just to remind you this is Z2. Okay, so in short, this essentially reduces the study of the identity component to the abelian case. Okay, and so this is determined by, but it's not true for, I mean, like that isomorphism doesn't extend, to other components. Okay, it's just this one component. Okay, so, and it's determined by the following. How is iota defined? You just precompose with pi, and remember pi was this map here, so that's why I labeled it earlier. Okay, so that's so you precompose with pi, and then that turns out it gives you a homeomorphism between the identity component and the abelianization of the Heisenberg group in the SU2. Okay, now let me say a little bit something about this space here, right? Because this space is not the same as this space, right? Of course, this space lives inside of here, right? Because T lives inside of there, right? But this is bigger, right? But the question is how much bigger, right? And so we can't say exactly what it is up to homeomorphism, but we can say what it is up to cohomological isomorphism. So let me make that a remark. I have a couple remarks, but let's just do this. So the first remark is that Z mod 2 into SU2 is let me use this notation for cohom. So there's a map phi which induces a cohomological isomorphism. So that means it induces a cohomology on isomorphism on cohomology groups with the space SU2 mod that maximal torus cross T2, but that's a little bit of a lie. You have to look at the quotient, a diagonal quotient of the Weil group, which is Z mod 2 in this case, where, let me tell you exactly what phi is. So phi takes a coset. So what do we have here, right? So we take a coset of maximal torus, right? And we have to have a pair with something in S1 cross S1, and then you have an equivalence class with respect to the Weil group. Okay, so that's what this bracket is representing equivalence classes, not pairs. Okay, all right. So So the equivalent class of a pair. Okay, and then T2 is 2 elements of S1. Okay, all right. And then what do? Well, we have to produce a homomorphism. So a homomorphism, though, by the evaluation map is just a pair of commuting matrices into SU2. So what do? Well, you take G, and you have to show this is well defined because it has to be up to the coset representative, but T's in maximal torus, so things are gonna, different representatives are gonna commute with these guys. Okay, so anyway, so you take G, and then you use that to conjugate T1, and then you conjugate T2 simultaneously. Okay, and with that you can show phi is a birational surjective desingularization. And moreover, it induces isomorphisms in cohomology. Okay. So that's nice. And so just a comment here, this acts freely. And so it, because essentially it's left multiplication here. So on that side. And so this is smooth, and so you have a free action. So this is smooth. So, and this is singular. So there's no way this could be, an honest homeomorphism. But the point here is that it's as close as you could get. Okay, it induces isomorphisms in cohomology, and it's an isomorphism off, Zariski closed subsets. It is surjective, and it's an honest desingularization map. Okay, so that's kind of nice. Okay, now that's the first remark. Okay, the second remark is that we can actually say something, this thing here is actually familiar. T maps into SU2, maps not into, sorry, that's false, maps onto that is the famous hop vibration. Okay. Oops. This is S1. This is S3. And you can show that's actually a two-sphere. Okay, so everything in this example is very, very concrete. Okay. All right, so I think that's enough about Hom. What section did I call that? Section 3. That was a longer section, right? Okay. Oh no, maybe there's one more thing I want to say about Hom. Okay, so the last thing in this section is what happens with the automorphisms. Okay, so the automorphisms of H act on the identity component by precomposition. So you take an automorphism alpha and you want to hit it with a homomorphism rho or representation rho. And then what do? You precompose. So you look at that rho composed alpha inverse. Okay. And this is well defined. Well, I mean, it's certainly well defined here. There's nothing else to say. But on the identity component, you have to say something, right? It's not much to say. This is well defined since automorphisms fix the trivial homomorphism and H is a continuous action. Okay, so since it fixes a point and it's a continuous action, then that means it has to fix the whole component. Okay, so that's the last thing I want to say about Hom. So now let's go to section 4, I guess, unless there's any questions. Are there any more questions before I go to the next step? No, okay. So here is section 4. This is a character variety. Okay. All right. So we're going to let math frac 0 be the connected component, the quotient of the connected component of the identity by SU2, where SU2 is acting on Helm space by conjugation by an element in SU2 acts on a representation rho by G rho G inverse. Okay. And so now we have, from the previous statement, we have a natural action of the automorphisms of H. We know what the outer automorphisms of H are. It's that the outer automorphisms are the quotient of the automorphisms by the inner ones, which are conjugation. We're quotienting the space by conjugation. And so, so then out H, which is, I already used the notation, but let me say what it is explicitly here. Then out H acts on the character variety. And I should have said this is called character variety. Okay. So out acts on the character variety by, well, you take a class of an automorphism and you take a class of a representation and you just take, you do the action we had here, and then you just take the corresponding class. Okay. Okay. Now there is, of course, you have to check that this is well defined, that, you know, in particular, you have to make sure that if you take, you know, an automorphism and an automorphism up to, you know, translated, say, by an inner automorphism, that you get the same resulting class. But that's sort of clear because inner automorphisms occur by conjugation. And so if you know, conjugate alpha, then this action would end up having a conjugate of rho of composed with alpha, and that would be in the same conjugation class of rho. Okay. All right. So in this particular case, we can say, so let's go back here. What did the Helm space kind of look like? It's not exactly this, right? But it's sort of morally this. Okay. And so what would happen if we quotient by conjugation? Right. Well, you see here, right, this map is essentially conjugating by this part, by this homogeneous space, which is homeomorphic to S2. So if you quotient by conjugation, you'd expect to only be left with the T2 part, but with this, of course, with that equivalence relation given by the Weil group. And in fact, that actually happens. Okay. So we could call it a theorem, although it's much more general that this happens for other cases. But let's just write it in this specific example. So the character variety is homeomorphic to T2 mod the Weil group. So this is, right, and just to recall here, this is S1 cross S1, and the Weil group here is just C mod 2. Okay. Oh, actually, you know what? Let me just write it out without annotation. S1 cross S1 mod Z mod 2. And you can show that this is actually a two-sphere. Now, it's a singular two-sphere, so let me draw a picture of it. It's usually called the pillowcase, although one of our audience members, who is now Dr. Segal Thomas, has suggested that we rename it the samosa, which I think is actually a good thing to do. Oops, because it does look, why is it keep doing that? Okay, it does look to me more like a samosa than a pillow. But anyway, but it strictly speaking is an orbifold. There are these singular points here. There's these points. Okay, but it is homeomorphic to a two-sphere. I'll write the traditional name for this thing. It's homeomorphic to a two-sphere, but it's not. But it is an orbifold. It has 4 orbifold singularities. But it's a good orbifold in the sense that its underlying space is a topological manifold. And you can be very specific about this space. We can write it as a set here as x, y, z in -2 to the 3rd power, such that x squared plus y squared plus z squared minus x, y, z minus 2 equals 2. Okay. This little function here is often denoted with a kappa, and it's very much related to the Markov cubic. And the way you should think, let me make a remark here. I don't know if I can get this in. You should think of x as equal to the trace of a, where what was a? Let's remember what a was. If we go back here, there it is. Pairs A, B that satisfy these relations. Okay. All right. And you should think of y as the trace of B and z as the trace of A, B. Okay. And kappa is the trace of the commutator. That's how you should think of it. Okay. So that's the character variety. Now, what does this action look like on it? Okay. So if we, because remember, this guy here is GL2Z, so it's a 2x2 matrix. Okay. So if we took A, B, C, D, in GL2Z, and you act on an equivalence class here. Okay. So you have 2 elements of a circle up to the Weyl group action, but remember those elements of the circle are actually diagonal matrices. Let's go back to that, right? They're actually here. Okay. So you have 2 pairs. So you have an equivalence class of 2 diagonal matrices in a maximal torus. But they're different, they're different So this is different angles. Okay, so let me just write this way. So this is in S1 cross S1 mod C mod 2. Okay. Right. Then how do you produce another element, right, in here, right? What does the action actually look like? Well, if you remember, we wrote down what the action was very concretely earlier. The reason why I did that was where was it? Right here. So there's some indication of where the calculation about the right now comes from. So you look at the class, right, of yeah. So how do I want to write this? Yeah, I'll write e to the I theta a plus I theta phi b 0, 0, and then I have to put the minus one there. Okay. And then the next one is e to the I theta c plus I phi d. Okay. Okay, so that should be what we would want, right? Because you take an element here and you hit it with an element here, and you should then get another element here, right? Okay. And so, and if we wrote this down, if we write this down in terms of the trace coordinates, right? If you think about what that looks like, right? We note that the output would be, x would go to 2 cosine a theta plus b phi. So x, right? Maybe I should write it more like this. X maps to that y maps to 2 cosine c theta plus b phi. Is that right? No, that's d. Sorry. And z maps, I think, to 2 cosine theta a plus phi b plus theta c plus phi d. Okay. All right. So so that's what the action looks like. But let's actually see what it really looks like. So let me make sure this is going to work here. Do you guys see this picture of the samosa?
Yes.
Yeah.
Okay, good. All right. So given everything's so concrete, you can actually just see what it looks like. So pick a random point on the pillowcase, yeah, and then just iterate the action, right? And to see what it looks like. And what happens is you see this. It does look like it's floating a little bit, but that's just because of numeric errors. Anyway, but the point is that it just looking at the forward orbit of a single point, it's going everywhere. It's wildly going all over the place. Okay. All right. So that brings me to the next section, which section is that? Section 5. Dynamics, I guess we should call it. Not really sure. So here's our definition. If and this is just a reminder, if people who study dynamics knows what this is, but anyway, so a measure preserving transformation T, and T is not the maximal torus anymore. It's just, it's a transformation, is strong mixing if for every for all measurable sets A and B, the limit as n goes to infinity of mu A intersect the transformation of B is, so you see where B maps to, is the product. Okay. And this implies, right, this implies ergodic. Okay, so an action is ergodic if you have an invariant measure with respect to the action and all measure invariant sets are either measure 0 or full measure. So you think of it like measure theoretically, like acting transitively, but it's of course not. Depending on the measure, it might not actually mean it's anywhere near transitive, but anyway, but intuitively, that's I think the way to think about it. Okay, so the theorem is that and this is the main theorem, this is 2021, me and Burelle. Okay, is that the example we just went through in detail is generalizes. So we let gamma be a finitely generated group and G a connected compact Lie group. Okay. If gamma is nilpotent, there exists a finite out gamma invariant measure on the character variety, which, since I didn't use exactly that notation, I'll tell you what I mean by that. It's the identity component of the Hom space mod conjugation. And that measure has full support. So that means it doesn't send open sets to 0. The measure of open sets is never 0. Okay. And second statement, and the more important one, if gamma, still assuming it's hyperbolic now, has an element, only one, not all, but just an element, a single element, without eigenvalues, roots of unity, in particular, element. Okay, but this is more general than that. I should say, in particular, if there exists a hyperbolic element, or in particular, if gamma is abelian, okay. Oh, sorry, should be a comma there. Then with respect to that measure, out gamma is strong mixing. And that implies, again, ergodic. Okay, so the example we went through was when G was SU2 and gamma was the Heisenberg group. It's sort of that's the simplest non-abelian Lie group that we can work with. And gamma being the Heisenberg group is really the simplest nilpotent group that is not abelian. Okay, and I illustrated what the action was, and you can kind of see explicitly what the measure is. It's, off the singular locus. It's the Lebesgue measure, because off the singular locus, the space is a manifold. And I demonstrated, at least with what the action looks like, and you can see it mixes things up a lot, at least intuitively from the cartoon, or not the cartoon, but the Mathematica demo. But then the point here is that it generalizes quite substantially to any finely generated nilpotent group, where there's at least one element that doesn't have any eigenvalues that are roots of unity. Okay, so when gamma is abelian, this is it has at least one free factor in the free abelian part. Then if it doesn't have any free factors, then the moduli, the connected component of the identity is trivial, and so this theorem is still stupidly true. But if there's at least one free factor, then this condition holds. But it's much more general than that. So that's the main theorem. But it's actually sharp too. So let me add a remark that if you look in the literature of nilpotent groups, there exists nilpotent gamma with all elements of out gamma having eigenvalues roots of unity. So this condition is not like we didn't just stop, working and just like, oh, this is the condition that works. Is that there's actually counterexamples. So there exists a gamma with all elements of out having eigenvalues roots of unity and a non-ergodic action. Okay, that's the first remark. Second remark is aside from abelian groups where the theorem always holds, there are, and the one example I illustrated, there are like infinitely many examples where the condition does hold. So so Heisenberg groups, not just the one, so the one we did was just the 3D one, but in general, for every n, there is a 2n plus 1 Heisenberg group. Okay, so we just did the n equals 1 case. So Heisenberg groups and all free nilpotent groups satisfy, and there's plenty more other nilpotent groups too that do too, but I'm not going to write them all down. We talk about it quite extensively in the paper. Anyway, satisfy the hypothesis of theorem. I already said it all abelian groups do too. Well, I should maybe be careful here. I should say the theorem holds for all abelian groups. Because it's not true that the hypotheses are true for all abelian groups. So finite abelian groups, the hypotheses will not be true for, but for finite abelian groups, the theorem still holds trivially. And then for any abelian group, that finally generated abelian group that has at least one free factor, the hypotheses hold. So hence the conclusion holds. Okay. So where should I end here, or do I have a minute or two more?
Yeah, I think you can go ahead. Please go ahead.
Hmm?
Please go ahead.
Oh, go ahead. Okay, I'm almost done what I had planned. So what? So where do you go from here with this? Well, so this is, what did I call this? This was the theorem, right? Verify dynamics. Okay. Right. And main result. Section 6, future work. So it turns out that hyperbolic surface groups and free groups, so that means genus 2 or more, free groups of rank greater than equal to 3, also.
Hi, Shane. Your voice seems very low. I don't know why.
Oh, what about now?
Yeah. Now it's fine. Now it's fine.
Yeah, I apologize. I think it's sometimes when I look at the iPad, I think the micro. So I have like the microphone's connected on my laptop, so it might be that my voice is like going down versus forward. So I apologize for that.
Sometimes it might be because it's not on focus. I think your screen, so the Zoom screen.
Yeah.
Okay. Well, okay. So hyperbolic surface groups and free groups of rank greater than equal to 3 also have out gamma. So gamma is one of those groups that oops. Acts ergodically. And both classes, hyperbolic surface groups and free groups of rank 3 or more, were first, or let me say both cases, were first shown for Lie groups G that were basically rank 1 or locally products of rank 1 groups, shown by Goldman. And then in both cases, the theorem was generalized to other Lie groups by other mathematicians. In the case of hyperbolic surface groups, this was Shah and I always forget whether it's Pickrell or I think it. I'm sorry, it's either Pickrell or Previtt. Okay, anyway, and Segal, do you remember?
Yeah, it's Pickerel.
It's Pickrell. Okay, yeah, sorry. Okay, very good. Thanks. Thanks for the assist there. So Shah and Pickrell generalized Goldman's case work there for groups that were locally isomorphic to SU2 to arbitrary connected connected compact Lie groups, and then Gellender generalized Bill's work for free groups, again from the SU2 case to arbitrary compact connected. Okay. So with that in mind, with these two classes, we say definition. We say gamma is Goldman if out gamma x on the identity component of the character variety for every x, sorry, I should say ergodically, with respect to a invariant measure of full support or with full support. So you could always put a Dirac measure at the identity because the identity is fixed, and that won't be very interesting. So we want measure of full support. Okay. Oh, and then the other thing, the quantifier for all connected compact G. Okay. And this is again here for, this is yeah, I'll just say it. So this is, yeah, for all connected compact G. This is true. Okay, so with that definition, so that remark, so we make a remark here with that definition. Hyperbolic surface groups, free groups of rank greater than equal to 3, and now from the theorem I just shared with you today from myself and J-P Burelle, we'll call them hyperbolic nilpotent groups. So they're nilpotent groups with a hyperbolic element in their outer automorphism group. Okay. Hyperbolic nilpotent groups are all Goldman groups. Okay, so the question is, can we classify or characterize the class of Goldman groups? Or even just, what are some other examples? I mean, what about not solvable groups or I don't know, polycyclic, or who knows? I mean, there's lots of classes of groups that are ripe for study here, and this is the beginning of a story, not the end. So I think I'll end it there. Just thank you very much for your attention.
Thanks. So, Lawton, so any questions? I have a couple of questions.
Sure.
So one thing
Crescendo showed up. Hi, Crescendo. Sorry.
Yeah.
Yeah. No, please go on. Yeah.
Yeah. So I was just wondering. So we are not assuming anything about semi-simplicity or reductiveness of G, right?
Of the Lie group. It's
Yeah.
just compact. Just compact is all.
Compact
connected.
and connected.
Compact and connected. Yeah.
Okay.
Yeah, that's the only thing that's being assumed about the Lie group. Yeah.
Okay. And another thing is also this the definition of character variety. We are taking the so just the normal quotient here, or we are taking the GIT?
Yes, that's because it's the compact case. So with the normal quotient, you don't need to do any GIT or anything because they're compact. All the orbits are closed already.
Oh.
Yeah, and the quotient's already Hausdorff for free because we're in the setting of transformation groups. So you don't have to do any kind of special thing for the compact group. Now, if it was a complex reductive group, now you have to start worrying about the quotient.
Yeah. And so the other question is, so this is on the identity component, we have this action ergodic, right?
Mm-hmm. Yes,
so
sir. What about the other components, right?
Yeah, so the Goldman.
Yeah. No, so it's a really fascinating question, and I mean there isn't that much known. So what we do what we do is for a special collection of Lie groups that are essentially products of SUP for P prime mod the diagonal action of the center. So that does include PUP. Little p is for the prime, right? P for projective, right? All right, it does include that case, but it includes lots of other cases too. For those cases and free abelian groups, so gamma is a free abelian group and the Lie group is those cases, we characterize what happens exactly dynamically on all the other components. And so it's really interesting when P is even, what happens is the components come out in pairs and the action just kind of flips the pairs on the non-identity component. But then what's even more fascinating is when P is odd, or it's an odd prime, it actually is transitive on all the other components.
Oh, okay.
And and the other thing to say is all the other components in the Hom space are like they are homeomorphic to things that look like homogeneous spaces, but in the character variety, they're just discrete points. So we have an explicit point count in those cases of the total number of components. There's the identity component, and then there's like this god awful formula in terms of the prime. Okay, I'm not going to write it down, but it's in the paper anyway. But and it's not our result, by the way. It's a result of Gomez and or sorry, Adem and some other, and some co-authors. I forget the list of co-authors, but Adem is one of the authors. Anyway, and anyway, so what we show is that so you have ergodicity on the identity component, and then on the other components is a set of discrete points, a finite set, and then if P is odd, the action is actually transitive on that collection, so it permutes each point to another point, and it's a full transitive action. And it's kind of, it was a fun calculation, but yeah, I knew I didn't have time to talk about that, so I didn't include that discussion in my prepared remarks.
Thanks.
How are you, Crescendo? Oh, disappeared.
Maybe I stop the recording.
Oh, sure, yeah.
Yeah.